Good morning, folks. This is George Scheck from Marcone Supply. Glad you can make it today. What we're covering this month is basic microwave diagnostics. Uh, what we've put together, or at least tried to, is a short program where even if you don't know a whole lot about microwaves, at least knowing the material that's in here, you would be able to diagnose several of the issues that you may run into on a day-to-day basis. Okay, the first slide that should be coming up is our safety slide, which we are required to show before we do any online presentation. Reinforces the fact that there's certain inherent safety issues whenever one disassembles or repairs a major appliance. Certainly care must be taken. Okay, questions. If you have any questions at all on the material that we're covering today, if you could kindly hold them till after the presentation. And at that point, just click on the raise your hand pad on your webinar control panel, and I'll open up your audio individually, and you can ask your question, and we'll certainly try to answer it for you. Okay, if you would rather not, or you have a question at a later time, by all means, just send it via email to that address there, george.schick@marcone.com. And here again, we'll try to answer it for you. Okay, models covered. Most types of models of microwave ovens. The results, the current readings that we get through this presentation are from a full size 10 to 15 amp microwave. If you're working on one of those little tiny things, obviously the current readings are going to be less, but they'll be in the same proportions as you'll see with the larger ovens. When you get down to it, as we'll see through the presentation, most microwaves are exactly the same inside, uh, minus all the fluff that they throw in there to get people to buy these things, all the bells and whistles, so to speak. So what we're covering today is basically geared to all microwaves. Equipment required for microwave repairs. It would be great if all the technicians had all this stuff. Some of it is kind of you gotta have it. Some of it is nice to have. Um, if you notice what's up here, the voltometer, you should have that anyway. Amp probe, same deal. This thing is very important to have, a line splitter. Okay, and here we have one that you can buy commercially. You can make your own. Get an extension cord and split the two cords apart and put your amp probe in there. That's a line splitter. This one, a little bit more convenient, a little easier to use, but nonetheless. A microlight, nothing more than a couple neon bulbs and a plastic enclosure. It's fantastic. You just throw it in the microwave, you turn it on. If the lights flicker and glow, hey, it's making microwaves. If they don't, it's not. Your mini breaker, what they charge for replacement fuses and these things. You don't want to keep popping fuses in while you're trying to diagnose the microwave. This is certainly handy to have. Thermometers, beakers that you have for water. You got to have a load in these things when you're operating them or testing them. Certainly, a plastic beaker is very convenient. Microwave leak detector. If you go by the FDA regulations, whenever you work on a microwave and the repair has anything to do with the door or the control, magnetron, You're supposed to take a microwave leak check after you're done. Whether you do or whether you don't, that's up to you. These are a Gobin anyway. It's fairly expensive. I'm sure most folks either don't have one or they have one that's maybe not as accurate as the one they show here. But nonetheless, something that you ought to do if you do work on a lot of microwaves. And by the way, all the part numbers that you see there, they're all GE part numbers. Why? Because they were available. You can get these things under any manufacturer name or outlet where you can get a good deal on them. Okay, first of all, what are microwaves? Microwaves are a form of electromagnetic radiation. That is, they are waves of electrical and magnetic energy moving together through space. Electromagnetic radiation ranges from the energetic X rays to the less energetic radio frequency wave used in broadcasting. Microwaves fall into the radio frequency band of electromagnetic radiation, and microwaves have three characteristics that allow them to be used in cooking. They are reflected by metal, they pass through materials like glass, paper, plastic, and they are absorbed by foods, the moisture molecules that are in foods. And there's where you see microwaves on the frequency spectrum, as they call it. Microwaves usually run at 2450 megahertz. That would be the microwaves in that little oven or the microwaves that they use in radar on Navy ships, 2450 megahertz. Okay, some normal operating characteristics of microwaves. Normal door conditions. These will not cause microwave leakage. Steam or vapor escaping from around the door. The door is designed to allow heat and steam to escape to prevent the overheating of the unit. It is normal to see some condensation between the door panels unless the condensation does not dissipate within a reasonable amount of time. Light reflection around the door or the outer case. The light that they're seeing is located outside the oven cavity and can reflect light out around the hinge, the door, the outer case, and oven lamp access cover. Excuse me. It is normal for the door to have some up and down or in and out movement. The microwave door does not have a gasket. It has what they call a choke that absorbs excessive microwave energy and does not allow it to pass. Okay, again, normal operating characteristics for fans and vents. The magnetron cooling fan will run continuously while the microwave is in operation to constantly circulate the air to cool the working parts, especially the magnetron itself. Okay, the vent fan on under cabinet models will make sound similar to a vent hood, your basic fan. This fan is controlled by a high-low off switch on the control panel, but will automatically come on if the cooktop surface below transfers significant heat to the microwave. The fan will not go off until the thermostat cools sufficiently. One of the big customer education calls for the under-counter microwaves is the customer claims that, hey, they're cooking on the stove below the microwave, and all at once the fan will come on in the microwave. And of course, she can't shut it off, and she panics, or he panics, and they claim something's wrong with the microwave. Actually, not. There's a thermal cutout or cut in, if you will, in the bottom of the microwave, those type of microwaves, to protect the electronics that are in there. Uh, that thermal cut in will close, turn the fan on, and other than unplugging the microwave, you can't shut it off until that thermal cut in opens back up after the uh, temperatures underneath it go down. Okay, the vent fan is usually a 300 CFM fan, so some smoke and steam from the front surface burners below will not be pulled into the inlets under the microwave. A warm outer case is normal from the heat generated from the high voltage components and from the food itself heating. Heat from the surface lights can make the cavity floor warm, especially if they're on for a prolonged period of time. Okay, lights and sounds, again, normal operating characteristics. A dull thumping sound or a hum while cooking at power levels other than high. When using a power level other than high or 10 or however they have it on that particular machine, the high voltage cycles on and off to obtain the lower power levels. This cycling causes this dull, thumping, pulsating, or humming sound. The low voltage transformer that powers the electronic controls and keeps time emits a slight humming sound that may be audible when the room is quiet. Dimming of the kitchen lights under low voltage conditions when you turn the microwave on or when it starts pulsating. Okay, the cavity light comes on when the door is open and while cooking. If the door is closed too easily, and this doesn't usually happen, the cavity light may stay on and the magnetron cooling fan runs continuously. A clicking sound from the control relays upon startup is normal. Okay, a couple other things. Arcing in the cavity while cooking. Arcing may occur for several reasons. Using metal cooking utensils can cause arcing to the metal cavity or door. If you have metal trimmed cups, plates, bowls, saucers, recycled paper towels may contain minute particles of metal. Grease or food buildup on the plastic parts can burn and arc. The shelf, some microwaves have a shelf that comes with it. They say it's for two-level cooking. The shelf should only be used in the microwave when cooking with two levels. For proper use, you need to have food on the shelf and the turntable below. If the shelf is left in without food on it, arcing can occur. By the way, that shelf, if you will, absorbs some of the microwave energy. So if your customer's complaint is, hey, it cooks kind of slow with that shelf in, yeah, it does. When the shelf is needed, make sure the metal cooking rack is firmly in place and seated properly. It has been found that some vegetables, such as green beans and carrots, may cause an arcing when cooked in the microwave. This is because of the iron content. Add more water to, your carrots and green beans. Poultry pins, twist ties, metal objects, kind of obvious. Okay, into the microwave itself, the high voltage power supply circuit. And this is, I like to have fun when I'm doing training. This is definitely not a fun thing. The high voltage in here can put you out of commission, especially if you have heart issues or if you have a pacemaker or something of that nature. You're looking at 4,000 volts in here with a fairly good amount of current. Service technicians should never utilize the voltmeter on any part of the high voltage circuit while the unit is powered or plugged in. Be very, very careful. Okay, the high voltage system. Okay, the magnetron tube requires a high voltage DC power source, usually around 4,000 volts DC. Voltage is supplied by what they call a half-wave voltage doubler circuit. And by that, they mean the high voltage transformer puts out 2,000 volts AC on its secondary, which is connected to a capacitor and a diode. Okay, the capacitor increases the voltage to around 3,600 volts AC from its peak voltage charging capabilities. The high voltage passes through the diode, resulting in a half-wave DC voltage applied to the magnetron tube. The negative output from the DC circuit is connected to the filament of the magnetron tube itself. The positive output is connected to the plate of the magnetron tube that is grounded to the chassis. The magnetron produces a high frequency radio wave, microwaves. By the way, just for your information, and several folks in the past have asked, what's a magnetron? It's a tube. It's a vacuum tube, like you used to have in the old televisions and radios. You have a filament in there that lights up, runs on around 3 volts AC, and you have a tube. The tube can become weak, just like the old vertical hold tube in the TVs. The tube becomes weak, the picture starts rolling vertically, and the vertical hold control. I know I'm talking Greek when I'm mentioning this stuff, but the vertical hold control doesn't lock in anymore. The tube is becoming weak, or the filament can open and it goes dead immediately. Magnetron, same thing. It's a vacuum tube inside there. Can go dead, absolutely, or as I mentioned, it can become weak and not put out the power that it was designed to put out. Okay, types of microwaves. Some microwaves are fed from the top using a stereomotor and blade to distribute the microwave energy. Some other types of microwaves may also have a turntable, but it's not required, so there could be an option pad on the key panel to turn it off. You only need one method to move those microwaves around or move the food around in the microwave stream. Some very or high-end microwaves may have both methods. Using if it has a stereomotor and blade and a turntable at the bottom, usually there's a pad on the control panel where you can turn the turntable off and on. It's not really required. Here again, it's fluff. It's an option to make it sell better. Other microwaves are fed from the side and do not have a stirrer to distribute the microwave energy. They do require a motorized turntable for even cooking. The waveguide has a mica or a plastic cover over it. Most often, this is on the side of the microwave cavity. Okay, I don't know if you folks ever heard of this, but there is a condition that can develop in a microwave. It's called superheated water. Not real common. Usually it gets the customer, not so much the technician. But if you have the proper conditions, filtered water, a container or a cup or something that is almost perfectly smooth, what could happen, and you put too much time on the microwave when you're trying to heat a cup of water, for example. What will happen is the water will heat past the boiling point, 212 degrees, without actually boiling. It'll just get hotter and hotter and hotter and hotter. And now they take it out of the microwave and somebody breaks the surface tension of that cup of water, and it basically explodes out onto their hands. And this is like a 5-second video, show you what it looks like. Certainly can happen. Not real often, very unusual, but it can. Okay, line splitter. We're getting into diagnosing these things. Finally, what they're using for just about all these readings, diagnostic wise, is a line splitter. Very important to have when you're trying to diagnose what's wrong with this microwave. Okay, current measurements, you have to use your amp probe. You have to have a line split, either with one of these commercial things, or like I said, if you split the two wires of an extension cord, um, whatever way. Okay, you want to plug the AC line splitter into the 120 volt receptacle. Plug the line cord from the load into the AC splitter socket. In other words, that orange thing is the splitter. Here's your cord from the microwave. Okay, they have the amp probe in the splitter. It says close the clamp-on jaws around either the X1 or the X10 arm of the AC line splitter. Okay, that's these openings here. If the X1 position is used, read the current directly on the meter. If the X10 position is used, divide the meter reading by 10 to obtain the actual current. The X10 is for reading very low current readings. If you're just reading microwave or any other appliance, you'll probably use the X1 position. And whatever you read, like say there, is what you're actually drawing. Obviously, the first thing you want to check for power at the outlet, you want to have 120 volts thereabouts. Excuse me. And the polarity should be correct. Okay, the little one here is the hot line, the big one, neutral, and of course your ground socket or ground plug. Okay, microwave troubleshooting using that line splitter. Okay, this is why you can make a diagnosis on a microwave fairly simple. I'm not saying the repair is simple, but the diagnosis might be made much more simple using this process or this procedure. Okay, you want to place a load. Now, as I mentioned, get a beaker full of water along with the microlight. Very important. In the center of the microwave cavity. Set the control for high power. Press the start pad. Okay, once you press the start pad, now you want to check the current draw on your amp probe. 10 to 14 amps current draw, and the lights are blinking. In the microlight, the microwave is most likely operating normally. That's what you would normally expect to get when the thing is working properly. Somewhere between 10 and 14, depending on what it would draw normally in a full-size microwave. And here they're showing about 12.2. That would be fine. And the lights are flashing. That means that microwaves are coming into the cavity. It's probably working okay. What if you're drawing 8 to 14 amps, but the micro lights are not blinking? What that tells you is the high voltage section is working. You know, your transformer, your capacitor, your diode, they're working. They're supplying high voltage. That's the load on the system. That's at 8 to 14 amps. But you're not making any microwaves. More than likely, almost always, the magnetron has failed. That vacuum tube has failed. It either died or the filament opened. You have a bad microwave, a bad magnetron. Okay, what if you do the same test and you're drawing less than 2 amps and the micro light is not flashing? And here we're looking at maybe 1.2. That means you have no 120 volts AC to the high voltage transformer primary, or the primary winding is open. And here you want to check, and I'll go over this a little bit more in depth towards the end of the presentation. But you want to check for 120 volts AC to that high voltage transformer primary. Do you have a bad primary, or do you have no 120 volts from the microwave system? But nonetheless, if you're drawing less than 2 amps, your high voltage transformer primary is not being energized, either because there's no AC to it or the winding itself is open. Okay, this is kind of an offshoot of what we were just mentioning. The microwave runs, but there's no heat. It sounds like it's working fine, but there's no heat. There's no microwaves. On some models, they have 2 fuses now on the filter board. The secondary fuse may have blown out. In other words, what they're using is a second line fuse to split the winding of the high voltage transformer. Okay, this would be for high power. In other words, you're cutting some of the winding out of the transformer, so you're generating a higher current because that resistance, if you will, inductance actually, is higher. So your voltage is going to be a little higher, your output voltage. And that's done with this secondary fuse. If you want low power, or I should say if the board wants low power, they would energize the full winding of the high voltage primary. Okay, you can check that without even opening the microwave. On models that have 2 fuses on that filter board, the secondary fuse may have blown. To verify this fuse is blown, turn on the vent fan, and then restart the microwave. If the current draw exceeds 8 amps, this fuse has blown. Very important. On these microwaves, and this is why, I'll explain why here. On these models, the high voltage transformer output and the current draw is greater when the vent fan is off. The secondary relay, let me see if we can do this. The secondary relay, this is what's feeding that fuse for high power. Okay. The secondary relay, high power, is energized, supplying neutral through the extra fuse, which taps the high voltage transformer primary winding, giving higher high voltage output. When the vent fan is turned on, the smart board changes relays, which bypasses the second fuse on the filter board. And again, try that. So the smart board, the power board, whatever you want to call it, is switching relays now. It's going through the secondary relay, which is powering the transformer, the whole primary. It's bypassing that fuse. When the vent fan is turned on, the smart board changes relays, which bypasses the second fuse on the filter board to keep the current draw low enough to prevent tripping a 15 amp breaker. The secondary relay, which is low power, is energized when using all the high voltage transformer, which draws a little less current. So when the customer is running the vent fan to make sure that the microwave itself doesn't draw more than 15 amps, it doesn't use that secondary relay, which incorporates that fuse. It's using the primary relay, which energizes the entire filament. So it's a good way to check if the fuse is blown. Turn on the vent and see if it works. Okay, back to using our splitter and our amp probe. You turn it on and you're getting 3 to 5 amps. And again, the micro light is not flashing, not blinking. You have a shorted diode or a grounded magnetron, which is unusual. More than likely, you have a shorted diode. May also have a loud 60 cycle hum. If you have that 60 cycle hum, it's absolutely a shorted diode. You want to unplug the magnetron and check each magnetron terminal to ground with an ohm meter. As I mentioned, that's kind of unusual. Can happen, but unusual. You should read open for each of the terminals. And at that point, you want to replace the diode. Okay, continuing with diagnostics. Say you're drawing 6 to 8 amps. No microlight. You have an open magnetron filament circuit or an open high voltage transformer filament winding. Either way, you have no filament to that tube. Okay, you want to check the high voltage transformer filament and secondary windings and the mag filament for continuity, approximately 1/4 of an ohm. Check the diode and capacitor also. Again, unusual, but possible for an open condition. 6 to 8 amps, you probably have a bad transformer. The secondary winding, the filament winding, is probably open. Okay, if you're drawing 10 to 14 amps, remember we drew 10 to 14 amps when the thing was working properly? You're drawing 10 to 14 amps, but the customer is getting poor cooking performance. Takes a half hour to cook a potato, or something that she would say is not normal. They cooked a potato in 5 minutes. Now it takes 15 minutes. You probably want to run the performance test. All microwaves are designed to run a performance test. This checks to see if it's working up to par. It's putting out the right amount of power. Usually the test is model specific. It's usually very similar to what I'm going to go through. What could be different is the temperature swing of the water that you're putting in there as a load. And this would be a normal performance test. Okay, measure the outlet voltage at the line splitter while running the test. This test is based on normal voltage variations of 105 volts AC to 130 volts AC. Obviously, low voltage will affect microwave power output and the temperature rise of the water. And they're kind of specific on the amount of water that you're using for that particular microwave. Most of them, again, they use 1,000 milliliters of water, and hence they use 1,000 milliliter beaker to make it easier to measure out. And you want to fill that to contain exactly 1 liter of water. That's 1,000 milliliters. The water should be between 59 and 75 degrees Fahrenheit. Again, you have to check it with your thermometer. You want to record the starting water temperature with an accurate thermometer. Place the beaker in the center of the cavity, set power level to high, and this is very important. Press time cook and set it for exactly 2 minutes and 3 seconds. Why 2 minutes and 3 seconds? You might ask. Well, it takes 3 seconds, thereabouts, for the filament to heat up enough in the magnetron tube for it to start producing microwaves. So basically, you're setting it for 2 minutes of actual microwave producing time. That's why you want to set it for 2 minutes and 3 seconds. Okay, then you want to press the start pad, carefully remove the beaker after the time has expired, and record the water temperature. As an example, and again, it varies from microwave to microwave depending on the power output. Obviously, it would be different from a 1,000-watt microwave to a 700-watt microwave. The temperature rise would be different. Normal temperature rise should be around 28 degrees at 120 volts at the supply, and 25 degrees if it was down to 105 volts AC. And they have it down here in red, so I can barely read it, but it says minimum temperature rise will vary by model and wattage. Refer to the text sheet for the exact spec for the microwave being checked. So what you're doing is looking at the rise, the temperature rise of that 1,000 milliliters of water in that microwave stream for 2 minutes. Okay, the microwave cooks unevenly. That would be the complaint from the consumer. Here again, place the 1,000 milliliter of water in the center of the microwave cavity. Place the microlight in several different areas of the cavity and run the unit for a short time. Observe the microwaves. Make sure they're reaching all areas of the cavity. In other words, if you put your microlight in one corner and it's glowing and flashing, and then you move it to another corner and it's barely even lighting, the microwaves are being distributed unevenly, hence cooking will be uneven. If they're not reaching all areas of the cavity, unplug the unit and check for a bad stirrer motor, blade, or turntable operation. Be kind of obvious if the turntable wasn't working. Not so obvious if that stirrer blade is not turning up in the top of the microwave cavity. Okay, check for a weak magnetron. If you think it may be, here again, run the performance test. You could have uneven cooking and the turntable and or the stirrer motor and blade working normally. It could be the magnetron itself. It's becoming weak. The tube is becoming weak with, could be age or use, and it's just not putting out the microwaves that it would normally put out. Okay, here's a common problem that it's easy to diagnose if you know what to look for. The microwave runs for a short time and then cuts off. In other words, the customer starts it up, it'll run for a minute or two, and the machine goes dead. I mean, dead. It stops, everything stops, and they can't restart it. Yet they let it sit there for a few minutes. Hey, it goes back to life, and she can restart it again. Normally, there's only one part in that microwave that'll cause that particular symptom. Okay, and that one part is the TCO, the thermal cutout that's mounted to the magnetron. Okay, let's see if we can do this again. Right here. That opens up because the magnetron is getting too hot. and it kills the L1 line of the circuit, the microwave circuit. It'll reset. It's the only TCO in there that will reset. And how do you know that? I think that's the question they asked on the next slide. But I'll jump ahead because I have this thing blown up. The bottom TCO. Look on the side of the TCO and you'll see ratings in centigrade and Fahrenheit. If, let's say, for example, the bottom TCO opens at 248 and it resets at 32 degrees, will that kitchen ever see 32 degrees or that microwave? Probably, I doubt it. The cavity TCO opens at 212, resets at 32 degrees. Will it ever see 32 degrees? I doubt it. Magnetron TCO opens at 302, resets at 140. Will it see 140? Yeah, we hope so, as it cools down. The code that they use for TCOs as to whether they're resettable or not is if it has a very low temperature for the reset temperature, it's normally not resettable. If it has a high temperature, it normally is. Okay, TCO, and they explain it probably better than I do. TCOs with a reset rating of very cold temperatures are not resettable. This cavity TCO trips at 112, resets at or below 32 degrees. The mag tube TCO will reset at or below 140 degrees. Yet not resettable, resettable. Check for and if you get this issue, it runs, cuts off, comes back to life, runs, back and forth. Check for proper operation of the magnetron cooling fan. Usually this is what causes it in most cases. That cooling fan that cools the magnetron down while it's operating has either stopped or it's running very slowly. Check for proper orientation of the exhaust fan, as some models use this fan to cool the magnetron. Poor or no air circulation will trip the magnetron TCO. Look for deformed or discolored wiring terminals, as they indicate a poor connection or a bad contact in the TCO, which could cause heat to build up and trip it. And you could also have a magnetron could be running hot and needs to be replaced. So if you have this issue, 9 times out of 10, you're going to have a fan or an air circulation problem. The other part of the time, it could be the magnetron itself. If you see the fans working fine, it's blowing a lot of air, and everything's fairly cool, but it's still tripping that TCO. Yeah, it could be possible the TCO was bad, but not likely. It's probably a bad magnetron overheating. But more than likely, it's airflow, the fan. Door switches. Okay, most microwaves have 3 door interlock switches. The door sensing switch is a low voltage signal switch that tells the main board the door is closed or open. Usually it's the top one on most microwaves. Usually they're mounted to a bracket, all 3 switches. Usually the door sensing is at the top. The door sensing switch is a low voltage signal which tells the main board the door is closed or open. The switch is closed when the door is closed and open when the door is open. When the door is open, the main relay on the board closes to turn on the cavity lamp. If the contact remains open when the door is closed, the cooling fan may continuously run. The fan's never shutting off. You might have a bad door sensing switch. Okay, the door sensing switch is normally open switch. When the door is opened, the switch opens, signaling the main board to close the main relay, turning on the cavity lamp. And you get this. Okay. Okay, that sensing switch closes that main relay and supplies the neutral side of the line, which turns on the cavity light. When the door is closed, the door sensing switch closes, signaling the main board to open the main relay contact, turning off the light, and it is okay to close the main power relay when a cooking mode needs to be started. If the contact remains open, as we mentioned, when the door is closed, the light will stay on and the cooling fan can run because the primary switch closes. And when they talk about a primary switch, they're looking at this here. Now you're turning on the fan and the light through and back to neutral. Okay, the primary switch is normally open. When the door is open, the switch opens, preventing line voltage from traveling to the high voltage transformer, cooling fan, turntable, and the stereo motor. When the door is closed, the primary switch closes, supplying line voltage to the high voltage transformer, the cooling fan, the turntable, and again, the stereo motor. Monitor switch. This is where we have some issues. Unlike the other two switches, the monitor switch is a normally closed switch. When the door is open, the switch is closed. The monitor switch is a parallel circuit to the high voltage transformer primary winding. The monitor switch does not operate any components. It's only a safety device. You go there to the customer's house, the microwave is dead. You find that the line fuse has blown out up here, and you replace the fuse and it works fine. You get back in your truck and you ride down the street, and she calls you on your cell phone and says, "Hey, it's dead again." And you go there, "Hey, the fuse is blown again." You put a new fuse in, it works fine, and on and on and on. The monitor switch, in a lot of cases, sticks. Sometimes it's open, sometimes it's closed. If that switch is closed, the monitor switch is closed, when you fire up that microwave, look at the circuit. You got L1 and the secondary relay closes. You got neutral going across the switch. Boom. Goodbye fuse. It's there for safety reasons so that the high voltage cannot start with that door open. That's its sole purpose in life. Okay, again, the monitor switch should a power relay be energized and the door is open, which puts neutral to the high voltage transformer. It will blow a fuse because line and neutral will be connected, blowing the main fuse. Some of these might be surprising. Microwave blows a fuse. What will blow the fuse on a microwave? Contact stuck on a primary door switch? No. Shorted high voltage transformer winding? Yes. Broken primary door switch? No. Shorted high voltage capacitor? Yes. Shorted high voltage diode? That's usually the one that most folks are surprised at. That will not blow the fuse. Grounded magnetron? No, it won't. Miswired high voltage capacitor? Probably yes. Stuck contact on the door sensing switch? No. Shorted magnetron? No. Open high voltage diode? No. Grounded high voltage capacitor? No. Stuck contact on the monitor switch? Yes, the one we just talked about. Microwave blows the fuse. When a fuse is blown, use that 15 if you have one, the 15 amp mini breaker in place of the fuse when testing. If the condition still exists, it will trip the breaker instead of blowing another, that breaker, not the house breaker. Instead of blowing another fuse, don't replace the fuse because of the cost of those things until the issue is resolved. The 15 amp mini breaker can also be used as a test jumper to test the operation of an open TCO. Microwave leakage test. And again, this is the instructions from this particular microwave test equipment. Place 275 milliliters of water in a 600 milliliter beaker. Place the beaker in the center of the oven shelf. If required, set the meter to the 2450 megahertz setting. This meter doesn't have that. It just works on its own. Turn the oven on for high setting for 5 minutes. While the unit is running, hold the probe perpendicular to the surface being tested and scan surfaces at the rate of 1 inch per second. Following the scan pattern, you want to test these following areas: the entire perimeter of the door and the control panel, the viewing surface of the door window, exhaust vents, and you see these arrows here. Minimum allowable leakage is 5 milliwatts per centimeter squared. You want to record that data on the service invoice. I've worked, and I guess I'm giving away secrets. I've worked on like a zillion microwaves in my life, and to be perfectly honest, I've seen one that leaked, that actually leaked, and that's because the customer pulled the chokes out of the door because they were unsightly and threw them away. Um, that leaked around the door. That poor customer probably has, 3 eyes by now, but that's the only one I actually ever saw that really leaked on its own. When a microwave door is replaced or impacted by a repair, the Food and Drug Administration, the FDA, requires that a leakage test be performed to ensure the consumer's safety. Service technicians should complete a leakage test and document the results on the service invoice. Again, maximum allowable leakage is 5 milliwatts per centimeter squared. And they allow me to put my own slide in here, just my own 2 cents for what it's worth. Again, back in the days, if you will, when we taught electronics to technicians and other folks, if you were teaching schematic reading, normally you would start at the beginning of the schematic and work your way to the end. And that holds true for everything but microwaves. If you want to save yourself some time and you're trying to figure out what's wrong with a microwave, you have this thing apart, uh, and you want to know where to go first, instead of starting at the beginning of the schematic, start in the middle, right there and there. Okay, as I mentioned earlier, just about all the standard microwaves are the same. They all have these 4 parts that generate microwaves: magnetron, capacitor, diode, transformer. All that all those four parts need is 120 volts AC to the primary of the transformer itself. All this stuff, and this is a very simple microwave, all this fluff, it could be lights and fans and GPS and TVs, it could be anything. In reality, all it does is supply 120 volts to that primary or not. Jeez. Or not. Okay, so if you have a situation where the microwave is making noise, it appears to be running, the lights on, the fans on, but it's not cooking anything. You may want to go to the primary of the transformer and measure for 120 volts. If you have 120 volts there, one of these four parts is bad. You don't need to go any further other than checking those four parts. If you have no 120 volts there, forget all this stuff. That's not your problem. Your problem's up here. For whatever reason, either it could be a primary switch, could be a TCO, it could be virtually anything. You have to trace the L1 and the neutral lines to the primary. But your problem's up here. Don't worry about the diode and the capacitor and the magnetron and the transformer. If you're not getting 120 volts, your problem's up here. If you are getting 120 volts and it's not cooking, it's down here. It's one of those four parts has failed. And if it's making noise and the lights are on, more than likely it's the magnetron. More than likely. Okay, just a few more slides on the 21st century technology microwaves. These started out as a big hitter, but they're not as popular as I thought they would be. Maybe give them a few more years and they will be. Inverter technology. We have inverter microwaves now, and I always got a kick out of the fact that you could tell a countertop microwave whether it was inverter or not just by lifting it. The inverter microwaves are much lighter than the standard microwaves, and I'll explain why in a second. You probably already know. Okay, microwave ovens with inverters. Conventional technology. Microwaves now and going back use just a single power level, which is regulated by switching pulses. It turns on that 120 volts or it turns it off. There's no in between. It's either on full or it's off. In contrast, inverter technology directly controls the power output. This constant soft penetration of microwave energy prevents the common problems of shrinkage, overcooking, and loss of nutrients. The result is even food temperature and textures throughout. And again, they give two examples. This is your standard microwave. As I mentioned, it turns on at 120 volts to turn on the magnetron to produce microwaves, or it turns it off. You either have it on or it's off. There's no in between. An inverter supplies a varying frequency which regulates power output. In other words, that voltage is not constantly on or off, it's varying. So they can vary the output of that magnetron instead of just turning it on and off. Traditional microwaves send out a single level of power in small bursts to cook food at different speeds. For example, when you set the power at 60%, the microwave energy would be on. The magnetron is on for 60% of the time, and it turns off 40% of the time. That's how they get 60% power. Inverter microwaves, however, give accurate, true, multiple power levels. When you ask for 60% power, the oven delivers 60% power. They don't just operate 60% of the time. This applies no matter what power level is selected. True power levels give you better cooking results, and your food would have an even texture and temperature after cooking. The constant soft penetration of microwave energy into the center of the food helps prevent overcooking on the edges and surfaces. And they give two more examples. This is your on the left here, your basic microwave. Okay, and again, you're turning it on at full power or you're turning it off completely. And they give an example as a gas burner. Either it's on high or it's off. No in between. The inverter microwaves, they can vary that power over extended periods of time. And again, comparing it to a gas burner, it could be on high, could be on medium, could be on low. Uh, it's always running. It's just running at different power levels. Inverter technology. An inverter equipped microwave ovens, the power transformer is replaced by a circuit board, which converts the 60 cycle incoming line frequency to a variable rate of 20 kilohertz to 45 kilohertz. A relatively small transformer is hence the weight is then required to increase the voltage to the level required by the magnetron. By varying the pulse width, the output power can be I can't say this word linearly controlled for more precise cooking and defrosting levels. The bulky power transformer is replaced by a small light wave circuit board, and because less heat is dissipated, the power efficiency is increased. Conventional technology uses just a single power level, which is regulated by switching pulses. In contrast, inverter technology directly controls the power output. Warning: discharge the high voltage capacitors. Just like the standard microwaves, these have capacitors in them. They're not as big, but they still pack just as big a kick. For about 30 seconds after the oven is turned off, an electric charge remains in the high voltage capacitors in the inverter power supply circuit board. When replacing or checking parts, remove the power plug from the outlet and short the inverter output terminal of the magnetron filament terminals to chassis ground with an EHS approved shorting tool or an insulated handle screwdriver to discharge them. Be sure to touch the chassis ground first and then short the output terminals. The output terminal is where that thing is pointing. Right there. That rivet looking thing. Okay, that's how you short out the capacitors or the charge on the capacitors on these circuit boards. Okay, this is just a layout of the circuit board. Heat sink. They got they got a thing with that heat sink, as you'll see in a minute. Your high voltage transformer. That's this thing, obviously. Your primary in the back here, secondary windings. C702, this is where you have AC coming in. C701, this is the pulse, 5 volts DC from the main board telling what power to run at. And this is CN703, that's your high voltage out to the magnetron, like on the standard machines, the two big red wires. Okay, your capacitors are down here. And again, the heat sink, very hot, charged with high voltage. Okay, a quick look at the schematic for a high voltage. I'm sorry, for an inverter microwave high voltage section. As we mentioned, it's a board now instead of those 4 parts that we mentioned earlier. Okay, you got your 120 volts in to the board. You have your DC pulse from the main board into the inverter, and you have your high voltage out to the magnetron from the inverter. Okay, the heat sink, and again, they're fanatical about this thing, these last couple of slides. has electrical potential to ground, high temperature after operation. There's your high voltage capacitors down here, and that shorting point, which they already mentioned, to discharge the capacitors. Okay, the inverter has high voltage and high current circuits. It functions the same as a high voltage transformer and high voltage capacitors in ordinary microwave ovens. So again, certainly care must be taken if you're anywhere near this board and that machine is operating. The inverter has an aluminum heatsink energized with very high voltage and high heat energy. It's hot in both respects, temperature and voltage. The inverter has a high voltage charge, which may remain in the capacitors on the board. They mention for 30 seconds, but just like the capacitor in a regular microwave, don't trust it. Discharge it just to be on the safe side before you work on this thing. And here again, they're fanatical about this heat sink. Do not touch the aluminum heat sink. It is energized with high voltage. It is hot thermally. And I know we all try to do things like this, but do not try to repair the inverter board. Replace as a complete high voltage inverter circuit unit. This is a replacement part only. Don't try to replace the resistor or the capacitors or whatever. Replace the board. It's not worth playing around with this thing. Okay, wish we could have went on for about 2 or 3 more hours, but unfortunately, that's the information we have on microwave diagnostics for the day. If there are any questions at all, by all means, raise your hand pad on the control panel there, and we'll try to answer them for you. Make sure you unmute your audio. That little microphone-looking circle, it has to be green for you to be able to talk through your computer. Okay, I'll scan through these, and if there are any hands, I'll open up your audio line after I call your name. Abraham, right at the top. Do you have a question? Abraham, you have to open your audio. Turn your audio on. All right, we'll come back to Abraham. Arthur. You have a question, Arthur? Arthur Weist? You have a question? Charles, you know how to work this, right?
Yes, sir. Good morning, George. How are you?
All right, how are you?
Doing great. Doing great. So 2 questions on the inverter. What's the best way to isolate the inverter to know if it's good or bad?
Well, it's kind of like if you're working on the inverter refrigerators. You have 2 voltages going to that inverter. You have 120 volts AC, and you have the DC. Usually, it's somewhere between 3 and 5 volts. If you have both voltages and you're not getting any high voltage out, there's a real good possibility you got a bad board. If you're missing one of the voltages, then you want to trace it back either to the one of the switches for the 120 volts AC or back to the main board for that pulse, that DC pulse.
Is that 701 and 702?
I believe so, yes.
And to ground that out, typically you're just going to use a screwdriver, but you're going to, how do you ground it?
Well, what I would normally do is get a jumper and put one end of the jumper onto the ground of the machine, the chassis, hook the other end to a screwdriver, an insulated screwdriver, and then just touch that rivet.
Okay.
And,
Okay.
and more than likely, it'll already be discharged. But again, don't trust it.
Okay.
The handle of it.
Thank you, George.
This long.
Oh, you're quite welcome.
Clear plastic. Ask him how to measure the output voltage, the high voltage.
You know.
You don't.
Well, how do we know that it's not putting it out?
Well, if you're putting it out, your magnetron would be running.
But if you're not, it won't be running.
So does an out meter or something, can you use it and determine if it's
It's basically the same as we just went through for a standard machine. If you're running the inverter microwave and you're drawing 10 to 14 amps, that thing should be running. That means your high voltage is running. If you're getting 10 to 14 amps and you're not producing any microwaves, you have a bad magnetron. That 10 to 14 amps is telling you the high voltage circuitry is operating and drawing current. So that magnetron should be working. It should be putting out microwaves. If it's not working. It's not the magnetron is not working.
so whether it's an inverter or a transformer, the test up front that you begin in the beginning should tell, it should be the same for both, correct?
Exactly, yes.
Okay.
What about using a kilowatt device instead of the clamp on amp meter? You know what I'm talking about? The little kilowatt. You plug it into the outlet and plug the microwave into it. You set it for watts, and it would tell you what the wattage is, the output.
I guess if you can convert that in your head to 1,000 watts or 1,400 watts, whatever it would happen to be, I guess you could use that.
Pretty cheap.
Something to measure the amount of power that it's drawing.
Okay.
They just have it set up. I guess the easiest we can possibly set it up is for current. So that's what they use as the measurement vehicle.
And I think that kilowatt device will allow you to use whichever setting you want, amps, watts,
Yeah.
voltage. Okay.
Yeah, you don't need a top of the line thing, to do this.
Great. Thank you, buddy.
Okay. Anybody else have questions? Let me go through this and look for hands. Oh, let's see. Tommy, do you have a question? Your audio's not open, Tommy. We'll come back. Anybody else have questions? Let's see. Arthur, we'll try you again. Arthur, are you there? This is great technology.
Hi, I'm here.
Okay.
I was just kind of, messing with the things. I don't have a question, but really good information. I've been around microwaves a long time, but you just kind of simplified it so much. I was always doing things like the hard way. But yeah, great information.
Thank you. Just to give you a little background on the way microwaves are in the hierarchy of repairs. Again, in another life, I worked in the TV shop, and of course you had to do so many TVs a day, repair so many, or they would yell at you. To make up, if you're having a bad day with TVs, to make up your count, if you will, we used to work on microwaves because they were so easy to fix. I think a lot of guys are maybe scared of them a little bit, not familiar with how they operate or what makes them work. But when you stand back and look at a microwave, forget all the fluff that they throw in there, the lights, the fans, whatever. The actual microwave is a fairly easy machine to work on.
No, that's true. And I've, of course, coming across microwave oven repair now is very slim, but people still want you to look at it. But yes, you gave me some really great tips. I mean, I know my way around a microwave oven, but really great tips on how to simplify the diagnostics, because it seems like today you're diagnosing the problems but doing very few repair work, because by the time you give them a price, they're like, just buy a new one, but they still want to know what's wrong with it.
Exactly. Usually the ones that have them repaired now are the ones under the counter, under the cabinets or built into the walls, where they're very, very expensive to begin with, and it would be a big hassle to replace them.
That's exactly right. If it's hard to get out of that, like especially if they have granite around it or tiles around it, the harder it is to get that microwave out, the more they're apt to repair it. But or they just don't want to buy it. They just don't feel like shopping for one. So.
Yeah, that would be me. Yeah.
But I appreciate all the information. You gave me some great tips. I appreciate it.
Quite welcome. Glad you can make it.
Thanks.
Anybody else have any questions at all? Anybody else? Tommy, are you there yet? Oh, well. Tommy was the last one. Okay, basically, that's it for today's session. They'll be sending out information on probably the first of the month for the webinars in May, the time, the place, the material. The recorded version, should you care to watch it, or maybe some of your techs couldn't make it, the recorded version of this will be up on the MSA Marcone website in its recorded format by close of business Friday, should all things go according to the schedule. So once again, thank you for calling in today, and have a good one. Take care.